We now discuss the proof of a theorem, and it is a result on matrices from the linear algebra, and this lecture is suitable for national eligibility test aspirants and PG students. And there was a question asked in CSIR National Eligibility Mathematics Examination held on 30th November 2020, and it is from the section B, and the question is on matrices and from the linear algebra. The problem is, let A be an n by n matrix of rank 1. Let alpha is equal to determinant of I plus A, where I is the identity matrix, and let beta is equal to trace of A. Then which of the following is true? The four options are given to us, and normally students eliminate options 1, 3 and 4 by giving counter examples and conclude that the option 2 is true, that is alpha minus beta is equal to 1. And that's all sufficient for them. But what is interested is to give a general proof for this result. And for this discussion, please consult this video which I have made for this problem, wherein I have also given a proof of the result in the general setup, saying that the option 2 is true was also discussed. Now I want to give another proof of the result, that is alpha minus beta is equal to 1, in the general setting using determinants. So that is the idea of making another video for this result. Let's now go to that result and discuss its solution. The theorem is, or the result is, let capital A be an n by n matrix of rank 1. Let alpha is equal to determinant of I plus A, where I is the n by n identity matrix, and let beta is equal to trace of A. Then we have to prove alpha minus beta is equal to 1. The proof of that theorem is now given. Solution. We have A is an n by n matrix, Aij n by n. Ith row, jth column, element is Aij. So this we have written as row 1, row 2, row 3, row n, where Ri is the ith row of A, which will be Ai1, Ai2, etc. Ain. We are given rank of A is equal to 1. So since the rank of A is 1, without loss of generality, we may take all the rows or the multiples of the first row. This you can do it without losing any generality. Let the rows of A be R1, R2 is C2 times R1, R3 is C3 times R1, Rn is Cn times R1, where Ci for I is equal to 2, 3, etc. n are properly chosen scalars. Then the matrix A will look like the first row R1, second row C2 R1, third row C3 R1, etc. nth row Cn R1, and that is equal to the first row is this, and C2 times the entries of the first row, C3 times the entries of the first row, etc. Cn times the entries of the first row. So this is A. We continue. So this is our matrix. So what is that we do? And the beta is equal to the trace of this matrix. The trace of the matrix is the sum of the diagonal entries, and that will be A11 plus C2 A12 plus C3 A13 plus Cn A1n. Now, alpha is given to be determinant of I plus A. So, the determinant of I plus A, you take A and add identity. That means the diagonal entries will be added by 1. 1 plus A11, 1 plus C2 A12, 1 plus C3 A13, 1 plus Cn A1n, and the remaining elements are all the same, and it is the determinant of. We continue. Now we take this, because it is a determinant, we want to evaluate it. So to evaluate this, I will apply some elementary row transformations on it. The first one is, from R2, subtract C2 times R1. C2 times R1. If you subtract C2 times R1, so C2 times, so you will get a minus C2 here. And if you subtract C2 times R1, this will cancel, and you are left with a 1 here. So like that, and from the third row, C3 times R1, etc. For the nth row, subtract Cn times R1. If you do it, let's see, 1 plus A11, A12, A13, etc., A1n, and C2 times of this is minus C2 minus C2 A11. So this will cancel. And minus C2 A12, this will cancel and 1 will remain. And minus C2 A13, this will be 0. Minus C2 A1n, this will be 0. So likewise, and from the third row, subtract C3 times R1. So you will get minus C3, 0, 1, etc., 0. And from the nth row, subtract Cn times R1, you will get minus Cn, 0, 0, 1. So this is what we have, and to evaluate the determinant, we have applied the elementary row transformations. By applying the elementary row transformations, the value of the determinant does not change. So that is the, after applying the elementary row transformation, this is the situation. And this is this determinant we have to evaluate. So how to evaluate? So we expand this determinant by the first row. And we recall, how do we write the expansion of the determinant of A along the ith row? This is a very well known result, what we have been using it. And determinant of A is equal to sigma, j is equal to 1 to n, aij into the corresponding cofactor, Cij. Cij is the cofactor of the entry Aij, where Cij, the cofactor of Aij, the formula is minus 1 to the power of I plus j into Mij, where Mij is the determinant obtained by deleting the ith row and jth column. So that is the one, and now we delete the first row and first column, and alpha is equal to 1 plus a11 times of this minor. So that is 1 plus a11 into this. This is the identity matrix. Now move further by first row means a12. That means delete the first row and second column. So what do you get? a12 into minus 1 to the power of 1 plus 2 into m12. m12 means after deleting whatever you obtain, that is what you have to write. So a12 into minus 1 to the power of 1 plus 2 into, after deleting whatever you get, that you write down. That is what? That is n minus 1 by n minus 1 determinant. Continue. Plus, so a13, delete first row and third column. Then it will be a13 into minus 1 to the power of 1 plus 3 into this remaining determinant. So this is the remaining determinant what we have written, etc. At the end, a1n, delete first row and the nth column. Then it will be a1n into minus 1 to the power of 1 plus n into this remaining determinant. a1n into minus 1 to the power of 1 plus n into the remaining determinant. So that is the expansion of that determinant by the first row. So this is what we have. Now we further write down the value of it. So alpha is equal to 1 plus a11 into this n minus 1 by n minus 1 identity matrix, that is 1. So that is. Now to obtain this one, minus 1 to the power of 1 plus 2 means minus 1 only, minus a12 into, what is that we do? To expand this, delete the first row and first column, then that will be minus 1 to the power of 1 plus 1 into this element, minus C2. And this is n minus 2 by n minus 2 identity matrix, that is 1. So that is minus a12, minus 1 to the power of 1 plus 2 is minus a12 into, you are expanding by this element. This element is 1 element. So minus 1 to the power of 1 plus 1 into this entry is minus C2. And what about this? Minus 1 to the power of 1 plus 3 is plus only, a13 into delete second row and first column. And second row first column means minus 1 to the power of 2 plus 1 into minus C3. So a13 into minus 1 to the power of 2 plus 1 into minus C3. And the remaining is the n minus 2 by n minus 2 identity matrix, and the value is 1. And here minus 1 to the power of 1 plus n into a1n, and now take out this row and the first column. What is this row? N minus 1th row, because it started with C2. N minus 1th row and first column, and that will be, cofactor will be minus 1 to the power of n minus 1 plus 1 into minus Cn into this n minus 2 by n minus 2 identity matrix, that is 1. So minus 1 to the power of 1 plus n, a1n, and you are expanding by this, and this entry is n minus 1 row and first column, therefore minus 1 to the power of n minus 1 plus 1 into minus Cn. So that's the expansion, and simplify, you will get 1 plus A11 plus C2 A12 plus C3 A13 etc. Cn A1n. And we recall beta is equal to trace of A is A11 plus C2 A12 plus C3 A13 plus etc. Cn A1n. So this will be equal to 1 plus trace of A. This is trace of A, that is beta, 1 plus beta. And alpha is equal to 1 plus beta. So alpha minus beta is equal to 1, and that is the result what we are looking for. And that is the most elegant proof of the result using the determinants. I hope that you have understood the proof of that general result, and I am sure you liked the proof using the determinants. I wish you all the best. Thank you.